Welcome to the BA webinar on multispectral imaging for analysis of Jupiter's atmosphere. We're broadcasting on Zoom with a live stream to YouTube, and the recording will be available to watch on the BA YouTube channel shortly afterwards. As always, you can ask questions by typing them into the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end of each of the presentations. It's my pleasure to hand over to Dr. John Rogers, the Director of the BAA Jupiter section.
Okay, thank you, Andy. Good evening, everyone, or good night, or good day, or wherever you happen to be. Now, I'll just get my screen shared, if I can. Share screen. Talk. And display. Okay, that's visible, I hope.
Yep, I can see that predicted vertical distribution of gases.
Actually, the start. Here we are. Okay, so in this webinar, 4 leading observers from around the world will be discussing what amateur images can contribute to the analysis of Jupiter's atmosphere by multispectral imaging. So, as you know, many amateur observers are taking these beautiful images in color, showing glorious multicolored clouds in different regions of the planet, and they change from time to time. But usually our analysis of the colors doesn't go beyond the descriptive. So we're going to ask, can we actually describe the colors objectively? What are these multicolored clouds? And also many amateurs take methane band images like this one here. In the methane absorption band at 889 or 890 nanometers, where features like the Great Red Spot and the equatorial zone are bright, and polar hoods as well. We know that those are largely high altitude features, but can we actually go beyond that to determine the actual levels of them and the relative heights? Well, it'll help to appreciate the following talks if I give you a brief introduction to what is known of the composition of the atmosphere and of the clouds. First of all, from theoretical studies, looking at the altitudes which clouds are expected to form. Now, we know that the atmosphere consists principally of hydrogen and helium, and other elements are present in, it turns out, approximately 3 times solar abundances. That is, they're in similar ratios to those in the sun, but 3 times overabundant relative to hydrogen. And from that, it's predicted that the main gases in the atmosphere will be water and methane and ammonia. And these are actually the observed mean abundances, very approximately in some cases, but from observations from spacecraft, including the Galileo probe and the Juno orbiter, as well as some ground-based professional observations. So theorists have predicted the cloud layers should begin just above 1 bar, that is exactly the same as Earth's atmospheric pressure at the surface, and should be of ammonia ice. Now, this chart, I should say, shows pressure increasing downwards down here, and temperature, which also increases downwards. So this region that you're seeing is called the troposphere, and in that area there can be convection, there can be weather, and that's where the clouds are expected to be mainly condensing. Below the ammonia ice there, it's predicted there'll be some ammonium hydrosulfide clouds, and below that a thicker region of water clouds, some ice, some liquid with some ammonia dissolved in them. And its base would be somewhere around 6 to 8 bars. How does that agree with observations? Well, this is a rough summary of observations from professional studies, both from spacecraft and from ground-based infrared observatories. There are clouds in more or less the expected levels, but only approximately, and there's still a lot of uncertainty about this. There is still very little evidence as to what the clouds actually consist of. Also, the studies don't completely agree about the levels, and they don't exactly agree with the predicted levels necessarily. And we don't know how deep the clouds go. Also, the clouds will vary with the regional patterns, such as belts, zones, Great Red Spot, and with the local weather. So there's a great deal more to be learnt about this. And let's look now at what might be learned in particular from images sensitive to methane and ammonia, which is what the subsequent speakers are largely going to be talking about. First of all, methane. Now, this does not condense at Jupiter's atmospheric temperatures, so it's uniformly distributed in the atmosphere, and its abundance is the same at all levels. So light in a band with strong ammonia absorption, methane absorption, such as the 889 nanometer band that I've been mentioning, like this image on the right, it can't penetrate very deep. So light penetrates down only so far as it can be reflected by high-level clouds and hazes. Ammonia is a completely different beast because it does condense at Jupiter's temperatures. It's predicted to form the uppermost cloud layer, and there should be at least some in lower cloud layers. And so the ammonia is expected to be of reasonable abundance below the clouds, but above the main ammonia cloud layer, there should be only a little of it. But it might be possible to detect some partial absorption by ammonia above that, which would actually be very interesting from the point of view of giving insights into Jupiter's weather. And now professionals, of course, have also made studies in these wave bands. I'm just going to show you a glimpse of those. But we must say that these also are quite uncertain in their conclusions, because it's very difficult to separate ammonia from temperature, cloud thickness, and so on. This is just a snapshot of some maps of the planet published by Dr. Lee Fletcher and his colleagues. This is a map of the 4.7 micron wave band, which is this thermal infrared, as these others are. This gives you a different view of the clouds, in which the clouds look dark, silhouetted against the glow of the deeper levels of the atmosphere, the thermal emission. At slightly longer wavelengths, some of the thermal emission is sensitive both to ammonia and to temperature. And so Lee has produced this map of inferred ammonia concentration, roughly where the cloud tops are. These red blobs here indicate that in the northern equatorial zone, there appear to be plumes of elevated ammonia concentration. But as I say, there are uncertainties about all this. And so another technique would be very useful, and that's what Steve Hill is going to talk about. So this webinar is going to investigate whether we can use the capabilities of modern imaging by amateurs with careful calibration to help answer these questions about cloud levels and gas abundances, and to see how they vary with time. Because amateurs have the great advantage of being able to continue observations with a given technique over multiple years and at frequent intervals. So if we can establish reliable measurements of these types, it should be possible to see how they vary with time, for instance, during the large upheavals that we observe in the visual range. So all of tonight's speakers are amateurs in this particular field and have done extensive work with carefully choosing their filters and calibrating their images so that they're a photometric standard. And then they can analyze their images by dividing them or subtracting them or recombining them in color to reveal aspects of interest. But I should mention as a warning that photometric analysis requires there has been no sharpening or elaborate enhancement of the images, such as is normally done for the sort of beautiful color images that you see. So many of the images that these speakers will show you will look a bit more blurry than usual, but that's necessary for the photometric analysis. So with that, I can introduce the first speaker, Christophe Pellier, who is a very experienced observer. He's also the lead author and editor of a major book on observational planetary astronomy, which, let's see, I can show you, there you are, in fact, if I stop sharing the screen, there you are, you can see Christophe's book there. It's very recent, 2020. It's thick, it's authoritative and definitive, and it's in English. So I highly recommend that book for anyone who's interested in planetary imaging or indeed planetary observing of any type. Okay, and Christophe has long been an expert in the use of color filters in his own observations and giving advice to others. And now he's developed a long needed method for calibrating color images so we can actually be somewhat objective about the colors that are being recorded. So I'm happy to introduce Christophe Pellier, if you would like to start your presentation.
Yeah, thank you, John, and hello to all. I'm going to share. Oh, do Do you see that?
Yep, I can see your slides now.
Okay, is it fine now?
Yeah, I can see the first slide, and yeah,
okay.
That all looks good.
Okay, thank you. So we are going now to talk about jovian colors. And the question is, why is it necessary or interesting to follow the colors of Jupiter? Since the colors of the planet show noticeable evolutions from year to year or in a matter of months. And a change of color can be linked to physical changes. For example, we have all observed fade and revivals of belts, reddening or brightening of red spots, or coloration events in the equatorial zone. Especially among amateurs, those changes are followed using subjective assessments and depends partly on non-uniform data. So there is a great variation of renditions between people or between equipment or methods. For example, if you use a color camera, the colors are not going to be exactly the same as if you use a black and white camera with filters. So there is a need to bring more objectivity, and there is also a need to measure or quantify the observed variations. So the relevant method of observation to achieve this is to calculate the albedo of the planet. The albedo measures the capacity of a solar system object to reflect the sunlight it receives. The essential concept is the geometric albedo. This is the ratio between the observed reflectivity and the reflectivity the object would present if it was a perfectly reflecting surface, and the albedo goes from 0 to 1. So you can see at left a simulation of a solar system object enlightened by the sun, and you can see that there is a gradient of light between the center and the edges. At right is a perfectly reflecting identical surface with a geometric albedo of 1, and the ratio between the two is going to give us the albedo. The method follows 3 steps. First, we are going to calculate through photometry the apparent magnitude of Jupiter in all the desired bands. Once the apparent magnitude is known, we can calculate which is called the normalized magnitude. This is the equivalent of the absolute magnitude which is used for stars, but applied to solar system objects. We calculate what would be the magnitude of the planet if the observer was located at 1 astronomical unit of the object and the object located at 1 astronomical unit of the sun. And you can see at the bottom what are the normalized magnitude of Jupiter. Under those conditions, it would be a very bright object. Then, once we know the normalized magnitude, it opens the possibility to calculate the geometric albedo. The geometric albedo, we are going to calculate it through equations found on some papers written by Anthony Malema and Richard Schmid, but we are not going to dive into this tonight. No, I'm going to be a bit short for method of observation. There are 2 methods. The first one is to do star photometry following the AVSO CCD or CMOS guide. This is differential photometry with correction of colors and magnitude, because the raw magnitude that you are going to obtain with your system must be corrected to match the reference system, which here is going to be the Johnson-Cousins magnitude systems. So in 2022, Jupiter was found at the same air mass than 2 stars in Aquarius, one blue and one red, and those were the references. The second method is a direct comparison between the magnitude of Jupiter and that of some of the Galilean satellites. This method is more experimental than star photometry, but it has proven useful many times. And you can refer to my EPSC work from last year. I'm not going to describe them here. But at the bottom, you have an example of an observation from 2021 in the red band, where the magnitude of Europe was 4.96, and then the magnitude of Jupiter in the same image was minus 3.20, for example. Here are the results from the 2 last years and the references. You can see that the results I have obtained are very close to the references, even sometimes spot on. Only the Z prime band is going to differ a bit. Now, these are the same results for the 2 years, but compare with the spectroscopic albedo taken by Erika Koschka. You can see that some of them are very close or identical. There are variations which are most likely to my eyes due to imprecisions and not really to variations. And to the contrary of what is usually done, the images are not filtered by wavelets or any similar filter. Only the stack of raw images is used. This preserves the natural reflectivity of the details. They are called photometric images. Below, you can see UV, blue, and red images that I've taken at my last stay at the Astrocaris Observatory last year. Photometric images are then sent into WinJumpos to be mapped, and this allows to eliminate the tilt of the planet that would hinder year-from-year comparisons and to create a regular scaling in latitude. The maps are then analyzed with the AirSpec software, and this allows to retrieve the photometric profile of the center part of the disk in the polar axis direction. Then the profile is calibrated in wavelengths from 0 to 180, and by doing so, it will be easy to scale it from one pole to the other. The profile is finally calibrated in albedo in a spreadsheet by scaling it through the albedo of the equatorial zone alone, and I will explain how we do that later. Now, here are some results. These are selected scans from the opposition of 2021. They reveal the differences of global contrast between belts and zone following each band of color. You can see that the global contrast is very high in the UV and blue light, but very low in red light. These are scans of imaging taken in infrared. It is also possible to do this in the Cousins infrared band at left, in the methane band at the middle, and the wide band at right. Now we are going to talk a bit about year-from-year comparisons. Here you can see two series of photometric images taken in the 2 years, and you can see that there are several differences that you can catch, and we are going to see if polar axis scans can actually help to detect and measure them. In 2022, the big and dark equatorial zone belt is partially gone. There is a fade of the north temperate belt, and you can see as well that the great red spot looks to have darkened a bit. So these are polar axis scans for the 2 years, and you can see that large variations are successfully detected in UV and B, while in red light, the changes are less detectable. And we are going now to try to measure the variations. If you compare the scans from 1 year to the other, and you can see that, for example, there is a great change in the equatorial zone. There is more than 2 points of albedo in the UV and 1.5 points in blue. And this describes the change in colors from deep orange to yellow, since the brightening is relatively more important in U than in B. The equatorial zone can sometimes present a white state where its albedo can reach up to 60% U and 70 or 80% in B. You can see also the NTB fade, which, by the way, would better be described as a brightening. And we can measure 1.5 points albedo more in U and around 1 more in blue. And to the contrary, there is a dimming of the subtropical zone with a drop of albedo of 1.5, both in U and B. Now we are going to speak about spectra of individual features, because axis scans are not suited to measure the colors of individual features, yet it's interesting to follow some of them, like the great red spot. We are going to use the photometric tool of the IRIS software. And by the way, this is how I have calculated the albedo of the equatorial zone. As an example, here is an image of the great red spot taken in blue light in 2021. The first steps, the software calculates the intensity of the globe as a whole, excluding the 2 moons from the measure and removing the value of the mean background. At the second step, we retrieve the intensity value of the great red spot using one smaller cycle. And the last step, The albedo of the red spot is found by calculating the intensity it would have reached if it had the same surface as the globe itself. Then taking into account the albedo of Jupiter in the band, which is 41% here, we can calculate a ratio between the intensity of that fictional red spot globe and that of the real globe. The value found here in 2021 that in blue light, the great red spot had the same albedo of the globe. And we are going to make a small interlude. How is it possible that the great red spot does not have a lower albedo than the globe in blue light, since it looks so dark? And the trick is that we must not forget that the geometric albedo is the mean value of all the points, and that the real photometric profile of Jupiter is not flat, but presents an important gradient of luminosity from the edges to the center. That profile is not perceived by our eyes, and whether it be at the eyepiece or on an image. And you can see that some points actually are going to reach a higher albedo than the mean value, and others are going to be to reach a lower albedo. And as a proof, here is the great red spot copied and passed on the limb. It now looks brighter than it is at the center. Actually, this is the same mechanism that will make a moon in transit being bright on the limb and then dark at the center. This is now the spectrum of the great red spot last year. So you can see that there is a steep increase from blue to visible and red, and this defines the red color. To the contrary, this is a spectrum of a subtropical zone of the same year when it looked bright on images as even maybe bluish. So you can see that it has a much higher albedo than the great red spot in blue and hue. And now here is an attempt of other feature, the oval BA and the brighter white spot 6. So BA is not red anymore and is brighter than the planet as a whole, even in blue and hue, unlike the great red spot. Now I will going to end this talk with color indices. The color indices are used as a measure of star surfaces temperature. The most common is blue magnitude minus visible magnitude. It is possible to apply the concept to albedo values and not only magnitude. So here you can see an example taken from the scientific literature. And the first one is blue minus red. This measures the drop of albedo from red to blue. This is the data from 2021, not 22. And you can read the graphic as the deeper the drop, the more intense is the absorption. So the more yellow, orange, or brown are going to be the color. Now this is the result for the next year. And you can see that the drop in albedo at the center, for example, is a bit less intense than in 2021. And the last color index is, for me, one interesting is blue divided by the UV. Because although images are similar in aspect, there are some differences between blue and UV. In UV, the upper haze that is almost optically opaque in the UVB, as you can see in the HST images below, that haze is already present in the UV we can observe as a matter, although it is translucent and not opaque. But this influences the albedo of strongly colored features, mostly the equatorial zone or the red spots. And such features are going to present an even lower albedo in the UV in comparison with other features. So, for example, here are the two indices from 2021 and 2022. So at left, you can see that there was a great increase of the index for the equatorial band. This is the huge bump at the middle. And there is still a difference in 2022, but more subdued. So the index for that band, that belt, was 1.4 in 2021 and only 1.2 in 2022. Okay, so I have finished. So if you have a question or suggestions, I thank you for listening to me.
Thank you, Christophe. For anyone wanting to ask any questions, you can use the Q&A button on Zoom. You can type your questions in there, or otherwise the chat. And if you're watching on YouTube, then you can type in the comments and I'll pick it up there.
Okay.
I thought it was particularly interesting seeing the optical illusion, because it really does, the great red spot really does look darker to the eye, even though when you shift it up, it's
yes,
but it is not.
Shall I kick off verbally while you're waiting for other people to submit questions? Thanks very much, Christophe. It's an excellent talk and excellent work. And if other people want to do the same kind of work, I mean, could you perhaps outline very briefly what they would need to do it?
Well, it is almost mandatory to get the filters from the Johnson Cousin set. So you can find those filters, but usually amateurs don't get them, with the exception of the UV filter, which can be converted directly. And actually, it is a bit more complicated to do than one would think. But I'm already, of course, to help any people who would like to do that, to learn the method. But basically, you can use whatever telescope you want, whatever camera you want, a black and white camera, not a color. But the only thing that you need to buy is the filters, the filters.
And do you have any sort of tutorial or any way of advising people if they want to start on this?
I've not really written tutorial on this because I am still myself on the learning curve.
Yeah.
But I'm ready to do this when I'm ready, of course.
If I can just ask one more, is it possible to do this analysis at all on earlier observations when you were not calibrating it at the time?
Yes, I think it's possible. Maybe it would require to reprocess the images the way I do it. It would be necessary to know the albedo of the planet at the time, but maybe we don't know that. But we can use the usual references to try to measure the variation of colors from past data. And we have also references in the scientific literature that we can also use.
We have a question which has come in from Bjorn Johnson. Is the spectral data available somewhere? It could be very useful when processing Juno images to check the color, for example, to distinguish changes on Jupiter from JunoCam changes.
If there is data from JunoCam, maybe, I don't know. Is that was your question?
Yeah, I think is the spectral data available somewhere? Is the kind of is how it starts?
Well, there is almost only one spectrum, which is that one taken by Garkoshka. I'm going to So do you see it? Actually, this is the most complete spectrum than we get. And it is not impossible to use such spectrum, but it would require a bit of a discussion of what you want exactly to do with it.
I know, but it might take Björn a little while to type. I know that he is processing Juno images in an attempt to show the true colors of Jupiter as it would appear to a human eye. Yes. And so I wonder if actually your data itself could be used, because as the spectrum will vary from year to year, with say like the orange equatorial zone, maybe your data itself could inform Björn's work for a particular year.
Well, I think that although you can use such data to objectively measure the variations, my point is I'm not trying to study true colors. For me, it's not really a reliable concept. It's much too difficult to define. For example, the colors that I obtain with the such filters are more yellow than most of images. And you can ask, are those images more real Then the others, no, they are not. For me, it's not really possible to define which are the true colors. You can just try to measure objectively the variations, but true colors for me is not a relevant concept.
And I think
it does not mean they are not objective.
Yeah, we're about out of time. We've got what might be a very quick question from Mike Caracas, which is it possible to do this work with an SCT, or do you need an all-reflecting telescope like a Cassegrain or Newtonian for the UV filters?
Well, you can use a SCT for any band. The UV is going to be a bit more difficult. Yes, it can depend on the telescope you have, because some SCT are correct in the UV, some are not very correct. So, but in blue light, for example, there would be absolutely no problem to use a SCT. And
John, with the other, we've got another couple of questions come in. Shall we take those at the end?
I think that's a good idea, yes, because we need to end the formal session at 8:30, but then the seminar can carry on for half an hour more informally for anyone who'd still like to join in any discussion or ask any more questions. So yeah, I shall move on now and introduce the next speaker, who is Stephen Hill from Colorado, USA, where I gather it's his lunch hour. Although he's doing this work as an amateur, he's a professional working in space sciences with a degree in aerospace engineering and a doctorate in astrophysics. And he's now working at the United States Space Weather Prediction Center in Colorado, where he leads the software development section. And also he's the lead scientist for the solar ultraviolet imager on some satellites of the NOAA. So as an amateur, he's using a typical amateur telescope as others do, but he's recently pioneered the use of filters for detecting ammonia in Jupiter's atmosphere. So I'd like to ask Steve to give his talk on imaging to retrieve spatially resolved ammonia abundance.
Thank you, John. Let me go ahead and share. Wrong screen. Let's see.
I saw your screen briefly.
Yeah, but it is not showing the presentation.
Are you expecting to see the presentation mode?
There we go.
Yeah, there we go.
That's it. That's fine.
All right. Terrific. Okay. Well, hello, everyone, and thank you for your interest in all of these great presentations. I'll be talking about measuring ammonia concentration in the Jovian atmosphere using a relatively simple technique that was pioneered in the 1970s. Let's see here. And the work wouldn't have gotten to this point without the help of many others. So I'd like to extend my thanks to John Rogers for all of his encouragement and helpful discussions. Also to Pat Irwin and Charlie Alexander for helpful discussions, along with access to VLT observations of Jupiter. And finally to Wayne Green of the Boulder Astronomy and Space Society for his support. And with that, we will move into the talk. So in recent years, there's been a renaissance in our understanding of Jupiter's atmosphere. This has come in great part due to large investments in facilities, spacecraft, computational resources, and human resources. Even so, professional investigations, while they produce exquisite results, can be limited in spatial and temporal coverage. And that's the motivation for this work, developing an accessible citizen science level effort to fill gaps and provide context and continuity for ammonia observations. I'll show how a small telescope can make meaningful observations of ammonia above the cloud tops, and also how the results are consistent with professional observations. So my equipment is indeed very simple and almost all available through commercial vendors. The aperture is only 0.28 meters. It's a Celestron 11 telescope, but it is sufficient to demonstrate the objectives. The suite of filters was obtained to measure the continuum and methane bands at multiple wavelengths and the ammonia absorption band at 647 nanometers. Over 62 observing sessions have been conducted, but only the observations in 2022 include the specific methane observations necessary for determining ammonia abundance. And you'll see that as we move forward. So in the 1970s, Combson and Krenes codified some guidelines to assess relative abundance of different gases by looking at adjacent absorption bands. adjacent spectrally. This is exactly the condition that we see for ammonia and methane in the red portion of the spectrum at 620 nanometers and about 645 nanometers. They're nice and close, and there's some flat spots that can be used for continuum measurements. So we add those continuum measurements, and you can see the actual filter profiles that I use on the bottom there. And again, this is the Karkashka spectrum at the top, a segment of it that I've been looking at. So because ammonia is variable and both horizontally and vertically, Woodman in 1977 wrote towards the conclusion of his paper that we may have developed a technique for studying local weather on Jupiter rather than a means for determining the planet's chemistry, which was the original sort of stated objective, was to look at compositional variations. So that's exactly what this work is doing. And as a final note, we've developed this technique to separate the absolute and relative calibration. This means that normal, uncalibrated, but linear lucky imaging data can be used. And I don't go into that in detail here, but if you have questions about it, I'm happy to share afterwards. So here are results from 2021 showing when we first really demonstrated we could see ammonia absorption, and we compare it to the visible and 889 methane appearance of Jupiter. The ammonia absorption is shown divided by the local continuum, so that kind of enhances the contrast to make things more visible. In both the methane and ammonia images, darker areas represent when more of the gas is present above the cloud tops. Positive correlations between methane and ammonia absorption show the dependence on scattering length, so are likely due to changes in cloud top height. If you see a negative or ambiguous correlation, say the ammonia image is bright in an area and the methane image is dark, then that means that there's something else at play, and you probably are seeing actual differences in ammonia abundance. So for example, if we look at the great red spot, it's showing reduced absorption in both methane and ammonia. That supports the idea that the great red spot has a high scattering layer. The clouds are high there. Conversely, the equatorial zone shows low absorption in methane, that is, it's bright, but high absorption in ammonia. That suggests that there's enhanced ammonia abundance there. The North Tropical Zone shows just the opposite, with high methane absorption and low ammonia absorption, suggesting depleted ammonia abundance. So that sort of spurred the work on further for the next year, where in 2022, we added a filter for the methane band at 619 nanometers. And this is what helps us meet that criteria for similar scattering paths like Holmes and Krenes. It allows the analysis to go beyond the ammonia absorption, the actual abundance of ammonia along the column in parts per million. The absorption looks mostly similar in both the ammonia and methane bands in the two left images. But when we take the ratio, then we're looking at the relative abundance of ammonia. And that's what's shown in the third image. Here we can clearly see the enhanced ammonia relative to methane in the equatorial zone, and also the depletion in the north equatorial belt. We see some suggestions of ammonia enhancement associated with the bright plumes, and we'll actually have a slide that zooms in on those later on. And note that the way this is presented, this is just the ratio of the images, and so we are still seeing enhanced ammonia relative to methane as dark. And we'll be switching that up when we look a little bit later. So the ratio of the transmissions shows us where ammonia abundance is high or low relative to methane. But how high or how low is it? To compute that, we need to be a bit more sophisticated. We use optical depth, which is directly proportional to the amount of gas. Then we include the effective absorption coefficients computed for each filter. That quantifies the amount of gas that's there. Finally, we need a reference value for the abundance of methane. This is well determined from many studies and was measured directly by the Galileo probe in 1995. Also, methane is a well-mixed gas, so it can be used as a reference everywhere on Jupiter. Comparing the ammonia absorption results from this work to prior work is straightforward. One way was to look at meridional profiles of absorption. The data is readily available in the literature, in this case, in the form of equivalent width of the ammonia absorption band as a function of latitude. It's easy to convert from optical depth in a filter to equivalent width. I created the data plotted here from an average of 22 ammonia absorption observations with an error envelope and compared it to a source in the literature. The shape of the absorption in this work follows that of Teufel from 2018. Note that they produced this data with the average of 12 long slit spectra from a much larger telescope. So we see pretty good matching of the absorption here. And again, that's very encouraging. Similar to the last chart, we can compare the column averaged abundance at specific pressure levels in the atmosphere. Here we see the meridional profiles from a mid-infrared retrieval of ammonia abundance at 3 pressure levels by Fletcher et al. 2020. We've averaged 8 of our observations from 2022 to obtain the blue profile, which is the column averaged ammonia abundance above the clouds. We can see that both the average value and the column average value of ammonia abundance and the contrast between the equatorial zone and the north equatorial belt are consistent with Fletcher's work. So our average in the blue and the values from about 650 millibars, they have a similar shape and similar values. So it says we're looking in about the right part of the atmosphere. So that's encouraging as well. Now we'll continue the comparison to professional work, but with 2-dimensional maps of ammonia. Here we look at the region of the Great Red Spot, which is well studied. The map on the left shows the ammonia abundance of 500 millibars as derived by mid-infrared observations made in 2014 and documented in Fletcher et al. 2016. And in this case, now we have brighter areas, hotter colors, reds representing enhanced ammonia and blues representing depleted ammonia. And the image on the right is, of course, for visual orientation. We'll fade the image here with one made from the average of 8 of our observations in 2022. And you can look for some similarities and differences. The scales have been adjusted to provide approximately the same range of colors, even though the absolute values on the scales are somewhat different. Note that we've got the ammonia depletion around the red spot and to its south and to the east. And that shows up both in our work and in Fletcher's data from 500 millibars. And while there are enhancements around the depleted region in both data sets, they have somewhat different morphology. Just going through the fade one last time. Note also that there's a 6-year difference in the observations. Sorry, I think that's 8 years if I did my math wrong there. Yeah, an 8-year difference in the observations. So, there certainly could be temporal changes there. What we really wanted to do was obtain data taken roughly concurrently with our observations, preferably from a larger aperture telescope to improve resolution and signal to noise. Well, thanks to Charlie Alexander and Pat Irwin from Oxford, we kind of hit the jackpot. They were able to provide an image cube from VLT using the MUSE instrument that was taken in September 2022. In fact, it was taken only an hour before our observation on the same night. By way of comparison, the VLT-MUSE combination has a similar plate scale to this work, but samples 3,722 filter channels simultaneously, which is just absolutely incredible. I used those channels to create synthetic images in the bands that I use, and then ran the data through the same analysis. And here we see the VLT-MUSE data run through the analysis that I've been conducting. So this symbol here, the average column abundance of ammonia is computed here by me, but using the VLT-MUSE data. And we can see quite a bit of interesting features here, and I'm going to fade back and forth between the VLT data and our average 2022 data. We'll also label some of the features. So now that we have data from the same year, it's clear that more of the features are similar between the two data sets. Of course, the 0.28 meter telescope without adaptive optics is far less sharply resolved. So as we fade one more time, I'll say that the most notable features are the depleted red spot, depleted ammonia in the red spot, the enhancement of the south tropical zone to the west of the great red spot, and the enhancement at the north rim of the red spot hollow. So these are very interesting things where, with further study, we can start to dig into the weather that's happening at the top of the cloud tops or within the column of Jovian atmosphere that we're looking through. Now that comparison looked pretty favorable, that we saw the same things in two very different observing systems, but our data was averaged across many observations to improve the signal to noise. The question is, what does a single observing session look like? And the fact is, it's noisier, but it still shows the same general features, maybe with a little bit more bumpiness spatially, but it's a good sign that we have the chance to look for variations over time scales of weeks using individual observations, not having to use seasonal averages. And then finally, we were lucky again. We happened to get two pretty good quality observations exactly 1 week apart in October. So we can look at the persistence and the change in the ammonia. This is October 13th and October 20th. And what you basically see, obviously the red spot depletion persists, but you can also see that there are features, not sure whether you can see my mouse as I'm mousing here, but to the upper right and to the direct right of the great red spot, there are enhancements that persist between the two time periods, even though they change shape and intensity. Similarly, to the upper left, there's also enhancement that persists but changes. So it's encouraging. It's just one time step difference that we have with good data. So we'll want to look at that more. And then finally, an important fact is that ammonia abundance varies both horizontally and vertically. We really wanted to make sure we're decoupling this from the distribution of cloud height. So we computed a rough relative cloud height using our methane filter and its known absorption cross-section. And we compare that to the distribution of ammonia here. So the first chart was the cloud height, where we're seeing high blue, the highest clouds are blue here, and the lowest clouds are red. And when we do the fade one more time, we can see that really that's not a direct correlation between the ammonia enhancements and the clouds. And in fact, we also saw some bright ammonia enhancements over plumes. So what can you do if you want to contribute observations? For the filters, you can use standard H-alpha filter for the red continuum. You'll also need 3 Edmond optics 25mm filters for the other bands. They fit in filter cells. When imaging, use linear camera gains and gammas. Don't sharpen the images. Keep observing sessions short. And I'm happy to provide more details on my algorithms, or for limited sets of data, I may be able to do the processing. If you want to share data with me, I'd love to sort of disseminate this and get observations that cover more time periods. And finally, just want to say this work has demonstrated the detection of ammonia absorption and retrieval of column averaged ammonia using small telescopes and other amateur equipment. We verified the results in multiple ways with professional observations, and we're poised to look for temporal changes. Next, we want to publish the work, look at and integrate the complementary atmospheric retrieval approaches, which are seen here today, and finally work with professional planetary scientists to understand and interpret the results. Please feel free to contact me at my email with any questions or suggestions. Thank you very much. And the last chart is the bibliography.
Thank you, Steve. John, to keep on time, shall we say if people have questions, they can do them sort of at the Q&A towards the end?
Yeah, shall we do one question if anyone has one at the moment?
Well, there's a comment from Patrick Irwin, which actually was from the previous one, but is relevant, which he was just saying the VLT Muse observations regularly observed Jupiter in the 475 to 933 nanometers with a complete spectrum for each pixel. So I think that's basically what Steve's been talking about here and linking in.
Right, yes. If I could just give one quick question that might be important for people. Can you give us a sort of rough ballpark of how much these filters cost, particularly that ammonia one?
Yes, all the filters, all the Edmond optic filters are about the same cost. The last time I purchased one, they were about $240 American.
Mm-hmm. Okay, thank you.
So we do have a question from Leigh Fletcher. Should we take that at the end of the session, do you think?
Let's take that now.
Okay. He said, Steve, this is great stuff. I think you're seeing the same north-south asymmetry in NH3 across the GRS, which has always puzzled us. Were you observing in July, August 2022 at all? JWST specifically targeted a GRS map in the mid-IR to map NH3 and H2O, PH3, etc., which would give another point of comparison.
Yes, I do have observations from July and August. I would have to look back to see which ones covered those longitudes on Jupiter and what coverage I have of the Great Red Spot, but I do have data from that time period.
Oh, that's fantastic. So yeah, and perhaps you and Lee can be in touch with that about that more either in the later question session or privately if Lee isn't able to stay around.
And what I would say is if people want to type questions during presentations, that's fine because we can come to them at the end.
Okay, I think we need to move on now. So I'll be happy to introduce Antonio Cidadão, who's in Portugal. His career is slightly parallel to mine because he also has a professional career in biomedical sciences. In fact, he's a professor of histology at the University of Lisbon. In astronomy, he was already one of the leading amateur imagers over 20 years ago. And he was then thinking hard about calibrating colors in images. Recently, he's developed techniques for imaging in methane bands to resolve the vertical structure of Jupiter's clouds. So I'll invite you now, Antonio, to give your presentation.
Okay, thank you. Thank you very much. I don't think that my screen is being shared. Try to do that again.
Not shared yet.
I was seeing what looked like a picture of your telescope just now.
Yeah, so we're seeing a picture of the telescope again.
Yes.
Yep.
Okay, so this is the shared screen where I'm moving
and I can see your mouse.
Yes.
Okay, that's great. So thank you very much. I'm very happy to be invited to this great webinar in the multispectral analysis of Jupiter atmosphere. While when possible, I try to obtain color images. I try to focus my attention to use various methane band filters to try to analyze the vertical structure of the Jupiter atmosphere. The filters vary in characteristics and they provide different images. And if they are calibrated, they can be combined, subtracted, they can be ratios that can be produced and then combined into false color 3D images to give some extra information besides the precious ones that also derives from individual filters. So this is the basic topic of my talk, which could not be, of course, be prepared without help of some of the friends that are here, namely John, namely Christophe, and namely Patrick Irwin, which shared with us his model, two-way transmission model along the Jupiter atmosphere to better characterize the filters and the filter response. So trying to give a very brief presentation of these topics, which are fundamental to understand the materials, the techniques that need to be used, and the results that obviously are different when different filters, different materials are used. So I'll try to use in various slides these two graphs, which come from the literature, from this West chapter, and from this recent long paper, which described the Jupiter geometric albedo along the spectrum, the methane capability to analyze different bar levels at the atmosphere, which is relevant and is related to the different methane absorption coefficients which vary along the spectrum. Also, this model of the clouds distribution and characteristics along the various heights and the atmosphere that are characterized by decreasing pressure along its way from the troposphere to the stratosphere. So methane band filters vary. There are various methane absorption bands. This one was mentioned just now in the last presentation. I have no experience at all about the use of this filter, but I recently tried to obtain also from Edmund a methane band filter with matched continuum that analyzes the 727 nanometer band. It allows to probe until 3 bar, so all these clouds and above structures in the atmosphere can be probed. But unfortunately, this is not a filter that has been used many times in amateurs. And it can be used with small size telescopes and gives very good resolution differences between the absorption results and the adjacent continuum probes. The most used is this one with a very high absorption band, which probes until more or less until 0.6 bar. So these clouds can be analyzed. These ones are almost undetectable. And there is another one at 1 micrometer, which also corresponds to a fairly strong methane band, which allows probing more or less to 1 bar in the pressure level. And that can be used also as a filter to probe the Venusian emission from the surface. So it is a filter with 2 possible uses in amateur astronomy. With these filters, we have to also obtain images with continuum. So selected bands where absorption of methane is minimal or absent, which can probe all the atmospheric features down to very low, very deep levels. And this from the correlation between continuum and methane band filters, that results can be produced and arise. For the amateur use, there also is the concept of continuum-like filters. This can be used perhaps in the first approach, but because they are broadband filters where mixed absorption levels exist or coexist, where its probing zone can be also obtained, but which are not true continuum filters. So when possible, they should be replaced by these passband filters with very definite contribution. So one other thing that has to be kept in mind is that the jovian albedo changes with wavelength. Christophe already mentioned this, but it is very dramatic, the albedo decrease at the various methane absorption bands. And this has to be taken into consideration when images are calibrated. Perhaps the reason for this to happen is that the cloud levels that the methane filters preferentially probe, which are hazes and also of course high altitude, are usually thin, whereas clouds at low levels are much thicker and much more dense. And today there is some of the results in the literature that say there is a planet-wide clouds or blanket of thick clouds that blocks most of the light coming to the deeper zones, that is placed more or less at this level, so at low tropospheric level. So everything that characterizes the various methane bands, the various differences in albedo that result from imaging on these bands, needs data calibration in order to subsequently produce math operations between individual filters. In fact, image data needs to be calibrated, and no processing can be done, for example, sharpening during this kind of analysis. Here at the top row, here are the images we are used to look at various forums, which are sharpened, which are scaled, linearly scaled, and even methane band filters appear as bright as broadband filters. Such ones are represented here. The reality is not this one. The reality is that when we calibrate, for instance, for the albedo of a Galilean satellite, in this case, Europa, for which I had the help of Christophe, which I thank, the result and the reality is completely different. This is the kind of images, calibrated images, raw images, non-processed, which can be subsequently subtracted or used to produce ratios between them to retrieve information. And when this type of operations is guaranteed, then we can pursue from individual filtered images, for instance, to perform subtraction between them, or even addition in some selected cases. And these images can be scanned and quantified to measure their albedo, either mean geometric albedo, or to analyze the albedo at various latitudes from north to south pole. They are different. These thick lines are from individual filters. The other ones are from math operations, and then they can produce valuable information that can change, and that I am very interested to follow in the next years to see if variations occur. This kind of math operations, which are here exemplified for the very strong methane filters, can also be applied to the continuum and to the 727 methane filter, giving rise to subtracting images, or ratio images can be produced, which various types of ratio that can be analyzed to retrieve information about altitude from these kinds of filters that can be retrieved. But filter characterization, not only center band, is crucial to interpret the results, because a filter is not only an isolated band. It is not an infinite small passband. It has an extended, even if it is 20 nanometers, it is an extended passband, and so the absorption, as it is represented by this data that was kindly provided by Patrick Erwin, is shown to vary not only at various levels of the atmosphere, but also along the spectrum. So to characterize each filter that we use, we need to average the passband of each filter we use, and from that data, obtained from various levels of the atmosphere, we have to produce this type of graphs where the behavior of the filters is referenced to transmission that occurs with the filter, and where it occurs in the atmosphere. Here you have an axis that represents height in the atmosphere. Here is an axis that represents transmission that the filter is able to produce. As you can see, the continuum filters remain highly transmissive at lower levels of the atmosphere, while methane bands vary with its characteristics, with each one that is used, but decay much rapidly and reach what we call an effective cutoff beyond it, where images are in practice not obtainable. But this cutoff is effective. It is not absolute. So processing artifacts easily occur, even if in this range of the graph, by overprocessing our images. So please, no processing of images for this purpose, please. Here you have various behaviors. The cutoffs at 0.6, at more or less 1 bar, more or less 3 bars, and the continuum and the continuum-like filters, which I referred, that in the first approach can be used, which have cutoffs at about 8 bar, which are much lower than the true methane band filters. As a side information for those that are beginning and already have the Sloan ZX and the Sloan Y filter, they roughly behave as continuum-like and as a filter which is similar to the 7-to-7 methane band filter. So as a first approach, they can be perhaps used by those that try to do this kind of processing. So while using always 2 filters in combination, it is very dramatic, the difference in transmission that occurs at the same atmospheric height. Obviously, and theoretically, there is also a difference between heights where the 2 filters should have the same transmission. But what occurs is that high features usually are thin and high and low reflectivity, while lower structures are very high reflectivity and thick. So this kind of information usually always is confused with this relevant information that I referred. However, the picture is complex because higher and lower clouds coexist in the Jovian atmosphere, and this has to be taken into consideration. So a few examples that it was possible to obtain.
It's been 15 minutes now, so.
Okay, so I'll do it fast. Some examples that occur with these methane band filters. These are the differences that occur between continuum and methane band at 7-to-7 nanometer. There are true differences, although while they are very faint. So try the Sloan if you have it. The differences between continuum and 889 are much more dramatic. And if you subtract both, you should have access to this level of clouds in the atmosphere. Between the 1 micron and the continuum, the difference is lower, but also allow us to probe this kind of atmospheric height. Of course, you also can have subtraction between 2 methane band filters, which can isolate this region of the atmosphere. And with these results, you can actually produce false color images where red can map deeper features and blue can map higher features. So in this image, you can find bluer or redder hues which correlate with height. This kind of this type of image was also used recent in the paper of Wang in an image from the Hubble Space Telescope. So the results or similar results with very different resolution, of course, can be obtained. If you change a little bit the combination, skipping the 889 nanometer and only using the 7 to 7 system and the subtraction between those filters, you can also have this kind of color-coded image that maps red, which is deeper, and bluish, which is more superficial. Of course, both types of ratios can be produced and analyzed to produce quantitative results. If you produce false color images with only the two methane filters that I first described, and the continuum light filter, we also can have this kind of data where blue is mapped to higher structures and red is mapped to deeper structures. And if the component images to calibrate to constitute this false image color are slightly different, for instance, using subtracting results from individual filters, mapping low, mid, and upper regions of the atmosphere, these maps can be also obtained and retrieved. For future development, what we are trying to do is using the Pat Irwin's modeling for two-way atmospheric transmission is to calibrate the individual in the original graphs, taking into consideration the differences in albedo for the different filters. And once we have this kind of calibration, we can perform and can simulate by these graphs the subtraction events that we are producing as images, and better characterize by analyzing these results which are the boundaries of the atmosphere which are being majorly observed in these composed images. And since these lines intersect each other, they can be used, each kind of this line and this line, for instance, if we subtract them, we can obtain a new image which tentatively is much more isolate, much more narrower in the atmosphere layers that are represented in it. Here is a mid-atmosphere representation, and here a much higher stratospheric representation. So basically, this is what I was trying to explain and trying to thank the help that you have given me, and trying to collect all the hints, all the help you can give me to pursue this work and eventually be able to publish it. So, thank you very much.
Okay, thank you very much, Antonio. That's a fantastic amount of work there. We are running a little bit behind time, so I think perhaps we ought to leave any questions until after the next talk, unless you've got anything very urgent there, Andy.
No, nothing coming. So yeah, if you've got questions, type them in, and we'll come to it when we have the general discussion and Q&A at the end. Okay,
well, let's move on then to our last speaker, who is Barry Adcock, who's out in Australia, where I think it's about 7 in the morning now, so I hope you've managed to have breakfast, Barry. A long-standing Jupiter observer, and been taking beautiful images for many years, but he's gone beyond the usual filter ranges that amateurs use to use multiple filters with sharply defined bandwidths across much of the infrared and ultraviolet ranges, as well as in the visible. And he's been doing false color combinations and subtractions to bring out subtle differences within those spectral ranges. So he has a calibrated record that goes back several years, which I think is likely to be particularly useful for analysis of the atmosphere. So without further ado, I'll ask Barry Adcock to present his talk on imaging in infrared and ultraviolet wavebands.
Thank you, John. my presentation is not as analytic as my colleagues, and I'd like to very briefly trace the history of what I've done. My adventures into infrared imaging started 65 years ago as a teenager, and I'm not going to bore you with the results. 1970, I finished making my observatory, although that's a modern picture of it. When I made it, there was no garden around it. And at the same time, I installed a 12.5-inch oblique reflector, the Cutter design, a Schiefspiegler, and I used that telescope to image the planets for the next 45 years. In those days, of course, our recording material was a film and wet chemistry, and even the new panchromatic film I've shown at the bottom there, most films had a spectral characteristic shown there, and it didn't venture much into the infrared at all. Although at that time I had put together an elaborate set of filters, either glass or acetate or gelatin filters, and I used those at the telescope. And using the Kodak Raton 47B filter in 1970, I was able to take a picture shown there, and you should note the size of the great red spot in those days. Later on, using a red filter, I could record different features as well. And I have a huge record of images of that type. If they're any good one day, we'll go through them all. In the time of digital imaging, like a lot of amateurs, I started with a Philips 2 cam, and a friend of mine gave me a Raton 87C filter, and its characteristics are shown in the graph here. Mr. Kodak has drawn a graph with the vertical axis upside down and also a logarithmic scale, but that filter is actually an infrared high pass filter. And again, during the early days of digital imaging, I was able to use that 87C filter to produce what was then known as pink pictures. And even at a glance, there are differences, of course, between the images, those two taken only a few minutes apart, but there are vast differences in the image itself. One of my aims in astronomy was to build a largish refracting telescope, and that's it there. And I have used that for the last 8 years in imaging the planets. And I put together a series of bandpass filters. I bought them from a company called Andover Corporation in America, and they actually have an Australian agent called Lastec in Adelaide. The filters there showing, I'm horrified to see that I can see dust on the surface of it. But they were 12 millimeters in diameter, and I mounted them in containers that we used 1.25 inch screw in thread. They're all mounted in cassettes or carousels that take 7 filters each. They're not motorized. I turn them by hand, and on a spectrum picture, the filters fit into that band range as I've shown there. Those are schematic diagrams, of course. The actual filter looks like that. They all have a bandwidth of about 40 nanometers, and going through the images from each range, immediately one can see differences. And one of the differences is probably a little bit difficult to see there is that at 800 nanometers, the image of Jupiter is always more contrasty than the others. And to show that, if we produce some red, green, and blue filters, we can produce a a coloured photograph of Jupiter, either with a black and white camera and processing like WinJupos, or we can use a colour camera to produce that coloured image. But if instead we use images at 600, 700, and 800 millimeters, what I tried to do very first of all is to move my eyes up into the infrared and have a look at exactly what the image looked like. And that's a colour image as if we were looking at Jupiter with eyes in the infrared region. Again, I emphasize that the image of Jupiter with 800 nanometers is always more contrasty than the others. And that's why that particular picture, red is allocated to 800 nanometers, and that's why it has a pink hue appearance to it. If you look at the great red spot, it's orange, and that means it's made up of red and a little bit of green, and there's no blue, and that's sort of confirmed from the images above. Allocating red, green, and blue to 900, 800, and 700 nanometers, 800 now being allocated to green, produces a picture of Jupiter with a green tinge to the background. Having a look at the methane filter, my filter is the narrowband one with 8 nanometers, and it is enveloped inside the 900 by 40 nanometer filter, and a picture of it there inside the 900 nanometer filter, and produces a picture of Jupiter at that wavelength. And looking at the others, it starts to show up the differences that Antonio was talking about. Yeah, differences. The image at 800 as a methane band and at 1 micrometer look quite similar, but in between, Jupiter takes on what I would call a normal, in inverted commas, appearance. And to look at this more analytically, we need a standard candle, if you wish, or a bandpass standard object to measure the brightness. And I know Antonio has used the satellite of Europa. What I have done is to try and keep the image processing the same. In the histogram, I have the same level, and the processing is kept to the same procedure, same recipe. The difference is, if we could divert a bit, if we could have a look at the planet Saturn in 2017, that shows that the difference between the bands is more outstanding. One can see that at 1 micrometer and 889 nanometers, 900 nanometers, the images are quite similar. And having a closer look at that, the image at 1 micrometer and the methane band are almost identical, whereas at 900, 950, it takes on a more common appearance. I've tried subtracting images, that image at 600 and the other one at 800 nanometers produces a difference shown there. And if you enhance that difference, it shows up the difference between those two wavelengths, wave bands. Moving on then, and I will only mention this briefly because Antonio talked about it at length. One can move our filters up to the far end of the infrared range, and that coloured image compared to the white light picture is recording red as being 950 nanometers, green 900, and blue at the methane band. And again, doing what Antonio has been working on, different combinations show up different differences in the appearance of the planet. If we have a look at that region there, there are vast differences in each one. And again, at that particular point, there are more differences in the composite images. And again, that shows the band taken image of the rest is the left is just a coloured picture of Jupiter, and then we move through the coloured bands to show the differences. And so the differences shown in yellow there, or in orange, are quite different from one image to the other. Moving into the ultraviolet region, white light picture of Jupiter is shown there. I have bought narrow band filters in the UV range of the spectrum, and if we combine those by combining red, green, and blue images again, Jupiter looks like that in the ultraviolet region of the spectrum. And even there are differences that one can see. The two north temperate belts are quite different from one picture to the other. Imaging in the ultraviolet end of the spectrum is particularly difficult. There's much less UV radiation reflected from Jupiter and than in the infrared region. That means the exposures are longer. We get less images to stack, and the atmosphere has a bigger chance to destroy the image. The cameras in general are not as sensitive at the extreme wavelengths using Barlow lenses, etc. It introduces spherical aberration, and I have found that many UV filters actually leak in the infrared region, and I have bought a Chroma Bessel U filter, which has the characteristics like that. It's one of the few filters that show the spectral response over an entire range, and an image taken in that filter is what I would expect to be a genuine UV image of Jupiter, although it is over quite a range of a wide range of bandwidth, about 80 nanometers of bandwidth. So it's not as selective as the other narrow band filters. Well, I noticed my time is just about up, John, so I might finish at that point and see if there are any questions.
Okay, well, thank you very much, Barry. That's a beautiful series of images you've got over these years. Yeah, are there any questions at the moment, Andy?
Nothing yet, but yeah, if you want to type in the Q&A, we'll also keep an eye on the chat. If you're on YouTube, you can type in the chat or comments there.
If there are no questions,
why not carry on, whilst, because it can take people a minute or two to type questions if they have any.
I've shown there the pictures of Jupiter taken in white light and at a band of 400 nanometers, which is the start of what we consider to be ultraviolet light in 2017, 19, 20, and 2022, just for a comparison. And that's where the shaded band of material down the equatorial belt appeared on Jupiter, and you can see that that's more outstanding in the in the UV pictures. Just looking into the future, I have put together a spectroscope, but I haven't persevered. Unfortunately, I haven't persevered with it for quite some time. It has that sort of resolution when you're pointing at the sun, although I know it can do better than that. They're the two double sodium lines that are in the spectrum of visible light. And that shows a comparison of Jupiter and the Sun over a fair range going into the infrared region. And again, I'll say I can do a lot better than that, and I'll try to do that in the future. And that's where I was going to finish anyway.
Right.
Okay, thank you.
Just to Patrick, I've now enabled the chat, though actually it's probably for questions, the Q&A works a little bit better than chat anyway, but the chat should now work. So we've got a question in from Kim Hay, which is, can you not use an IR filter to take out the IR that is leaking? I guess that's an IR blocker filter, which she means.
Oh, yeah. Yes. Well, an IR blocking to take ultraviolet pictures, you've got to use what they call an L filter, and that blocks some infrared, but it allows ultraviolet light to penetrate the filter. But I'm suspicious that the filters still leak at some point, and I reckon that some of the UV images do contain a little bit of contamination from infrared leakage. Of course, the infrared blocking filter only starts at about 650 or 700 nanometers, so it is possible to have quite a leakage area in that as the beginning of where it blocks.
And we have a question from Patrick Irwin, which is, have you recorded images in the same sets of filters of the many years you have been observing, in which case this would make for quite a historical record?
Yeah, well, I have a record of everything I've done. So I guess it does represent a comprehensive historic record.
I guess, does that then, the same filters used over many years, and so kind of therefore they're comparable?
The problem is going back to the film days, I experimented with various films, although I did concentrate on Ilford FP4 for a lot of images. But then moving into the digital age, the cameras change and get better, and the telescopes change and the techniques change, and it's rather difficult to say that the same technique was used over decades.
But I think you said you started your present technique in 2015, right? Your present telescope and filter set. So it's fairly uniform since 2015.
Yeah.
Well, that's great, because that covers the whole Juno mission and a couple of cycles and of activity in some of the major belts and zones. So.
Yep.
We have a question from Stuart Beveridge, which is, when imaging in the UV, what is the average frames per second and exposure settings you use?
It's not good, but down at 350 nanometers, one exposes for over 1 second. And in a 2-minute exposure, that means we only get less than 120 images to stack. One may stack probably as many as half of them, but in that second, of course, it gives the atmosphere a good chance to destroy the image anyway. So down the infrared region, hopefully the modern cameras will become a lot more sensitive in that region. Perhaps at multi-$1,000 work, they already exist, but for amateurs in the order of several $100s, I hope they improve in the future.
Okay, any other questions specifically for Barry?
Nothing coming in for Barry.
Well, perhaps we should first ask if there are any questions specifically for Antonio, since there wasn't time to...
Shall we bring everyone back in? And
yes, that's
Barry, if you're okay to stop sharing, then we can kind of do a everyone can appear if they wish to. So we do have a comment from Patrick Irwin, which was fantastic progress, Antonio. Really very impressive. And then right on the Christophe's presentation early on, just let Christophe get back up.
Yes, so I can read the question.
Okay, yeah, and it's from Bjorn Johnson. It is the year-to-year variation of the spectra that he's interested in.
If there are some spectra taken from year to year, I am not aware of that because maybe it's more professional data. So I personally don't have such data.
At least, Christophe, you have the 2021 and 2022 data. So there has been some changes just in that period.
Yes.
I mean, if I could ask Antonio, which of the various sort of combinations you use, such as subtractions, do you think is most useful for distinguishing the different layers of the clouds and hazes on the planet?
Well, the subtraction between a continuum or continuum-like, that was the filter that I used sometimes until now, and the one micron methane band filter provides a preferential view of the deepest visible cloud layers, but also gives rise to some potential artifacts because what is subtracted are not the very thin hazes that exist in the stratosphere, but also some lower altitude haze clouds that can produce an over subtraction effect and some kind of negative-like effect. Use that kind of subtraction with other combinations revealing higher level clouds to give interesting results. But I would say that besides that, and trying to avoid those kinds of artifacts, subtraction works better with thin layers of hazes, which are higher altitude. So also the subtraction between the 189 and 1 micron filters would produce very interesting results.
But maybe we could go back to one of those images that you showed.
Okay.
Is it possible to share your presentation still? Is it around?
I'll do it.
It was also interesting to see your false color images because they went past, we had to go past them rather quickly.
Okay. So I'll just try to start the screen sharing.
Well, I think some of the false color you did could also be used with Barry's if it doesn't involve complicated subtractions and so on.
Yep. So this, for instance, this kind of subtraction also seems to be very interesting. But this is a new set of filters that I don't have that much experience so far. Which is this kind of subtraction. This subtraction was made between calibrated continuum and methane filters. So, but you can see that there are some areas which are preferentially at the zone belt interfaces or within the belts themselves that pop up as small scale lower clouds. The problem is to know or to define which is the true height of these clouds due to the concept that there is some blanket of high thickness clouds at about one bar. So I wonder if these clouds which are being seen here, although these filters have the ability to probe deeper than 1 bar, are really below 1 bar or just above that generalized planetary optical dense cloud blanket. But this can be seen very well through subtraction and also through ratio. So this kind of mathematical operations seem to be very interesting in the future. Besides that, I think that this type of results between a very deep indivisible cloud layers, but very deep through this subtraction. So a continuum-like, which is subtractive from some filter that probes until 1 bar, produces really nice results and informative results if combined with other layers of the atmosphere.
I think, does Steve want to make a comment there? I noticed you've got your hand raised.
Yeah, this work is absolutely wonderful, Antonio. I did some experimentation with some of those same bands, but it was not the main focus of my work. I was looking at ammonia. But I wanted to say, given the fact that you've looked at and computed the two-way transmissions for the different bands, and you've done the subtraction work, etc., have you thought about trying to retrieve the actual sort of effective cloud height based on a reflecting layer model to get a quantitative answer in each of the bands? And of course, realizing it'll be different because it's looking at different kinds of hazes and clouds in each. Just curious as to whether that's a direction you think you might go.
Yes, I would like to do that, because even the model that I have tried to explore a little bit, and that was provided by Patrick, only refers to one inclination, so one light geometry. But if the images are corrected for the albedo that is observed, perhaps these functions can be used to retrieve actual altitude. I would love to do that, and I would like very much to be tutored to know how to do that. Yeah. Yes, absolutely.
Thinking about what other amateurs might be able to do, with the slide you showed previously, I think it's something that that Barry could produce, the false color picture. And it's not it's more discriminating than if you simply use the 3 filters on their own for the 3 colors in false color, but it's qualitatively similar to what you get if you use just the continuum like and the 1000 nanometer and the 89 nanometer, isn't it? So Barry can use those same 3 filters to produce false color images.
Yeah.
Mm-hmm.
And I think you do see some interesting color variations within this image. You're certainly seeing different cloud levels in the 3 colors, especially in the equatorial zone there, where you're putting your mouse. It's fantastically intricate variations in the cloud textures there in the equatorial zone.
Yeah, which also can be observed in the 727 model, even because the filters which are involved in this kind of image intrinsically provide much small scale detail than the methane filters, which probe higher levels, which detect hazes. I think that this was obtained in early February, so Jupiter was small in apparent diameter at the time. So I think that during opposition, this type of filters, which with good seeing, can really produce interesting images from small scale cloud variation at the levels that can be probed by these filters. So about 1 bar, 3 bar, more or less.
That's also an interesting combination of filters, because as you mentioned, that's also the filters that have mainly been used with people, professionals analyzing cloud heights from spacecraft.
Mm-hmm. Yeah.
Steve, is your hand up because you still have a question? Or
Oh, no,
oh,
there we go.
does anyone have any more questions for Steve? Because you didn't perhaps have a great deal of time for questions either.
I have a question, if I may, for Steve, because he uses continuum not only for methane, but also for ammonia studies. And my question is are there any specific or some kind of potential continuum bands that corresponds to absorption bands for the other molecule? For instance, some continuum methane filters cannot be used or should not be used in your kind of study because they are close or correspond to an ammonia absorption. Are there any specific wavelengths that should be avoided when trying to select the best continuum filter?
Yeah, certainly. Can I share my screen for a sec?
Sure, yeah. Antonio, you'll have to unshare yours.
Okay, done.
So basically the continuum filters, at least in the region I'm looking at, are the ones that are color-coded blue here at the bottom. And the only problematic thing is in using H alpha, you've actually got part of the 668 nanometer methane band impinging on that. So that band starts, that's why you see two curves here for a continuum model. The orange represents really closer to the true continuum of Jupiter if there were no absorbing gases. But the blue dotted line is sort of the more practical one that allows you to extract the ammonia absorption, because that band of methane at 668 does extend down and overlaps a little bit with the red end of the ammonia band. So you have to be careful with that, and that's an error where certainly there could be some potential errors. If you look blueward of the CH4 line band, like around 610, 605, that's really clean continuum, as is the middle between 620 and 645. That's really clean continuum. And so I actually am thinking about adding a filter to the blueward of the methane band just to be able to do better interpolations for continuum. So does that kind of answer your question, or were you thinking of the longer wavelength bands like around 940? I know there's a methane and ammonia overlap.
But you didn't use those longer wavelengths for ammonia so far because of the CCD or SMOS.
No, I didn't use them because they're not as clean. There's more overlap between ammonia and methane there. And so it would take a little bit more to separate them. I'd probably have to create a linear combination model to extract the strength of each one, which I'm kind of on the verge of doing, but I haven't yet. And the longer wavelengths do have the advantage of greatly reduced Rayleigh scattering, which is an effect that contributes a lot to the reflected light, even in the red. But when you go to the infrared, it goes down even more.
We also have a comment from Patrick Irwin. John, I'm not sure if we want to offer to Patrick for him to join the panelists.
Yes, if he's still here, yes.
Yeah, if Patrick, I'm not sure, would you be happy for me to promote you onto the panelists where you can speak, and if you wish, share your screen? I'll let Patrick type if he's happy for that. What I'll do is I'll just read out. Oh, yes, I'll go ahead and hopefully this should just work. And in a moment, Patrick shall join us. Here we go. Great.
Hello.
Hello.
Hi, Patrick.
Hi there. Thanks for inviting me on.
Oh, you're very welcome.
Well, thank you for all the help you've been giving to some of these people doing these studies.
Oh, it's been an absolute pleasure. It's I'm just it's gobsmacking what you guys are doing. Just unbelievable. It was yeah, amazing.
Should we read out your comments since you bothered to write it? It was
Sure.
talking to Antonio, I think, saying the atmospheric seeing gets more favorable at longer wavelengths, which is probably why the longer wavelength images of Antonio have higher apparent spatial resolution.
Yeah. It's just a comment. So that's that obviously the seeing is worse at blue and gets more favourable as you go to longer wavelengths. And so the longer wavelength observations, if you've got a big enough telescope, tend to be clearer. Yeah.
Well, I'll make a comment on that. Fundamentally, the resolution of telescopes is higher at the blue and ultraviolet end. If you theoretically had perfect seeing, like if you had a telescope on top of a mountain and very good seeing, and you occasionally do see that from some images, that occasionally they do manage to produce blue or ultraviolet images which are as good or better than red images from the same telescope, but it's unusual. But there's various complicating factors, like the sensitivity of cameras gets much less in the very long wavelengths, or when you get towards 1,000 nanometers. So then you need long exposures. So that starts to mitigate against getting sharp images at the same time. So there's probably, in my experience, the sort of optimum for sharpness would be around 700, 800 nanometers.
There's also the point that I think Steve raised that the Rayleigh scattering gets less as you go to longer wavelengths as well. So that also contributes to the images being more clear at longer wavelengths.
Antonio, have you seen much difference in resolution between your images at different regions of the infrared?
Yes, not only differences between resolution, but also between signal to noise ratio. That's a really important. Not only for single filtered images, but also for subtraction or for image ratios, where the noise steps up really rapidly. So I think that with a standard night or a standard conditions here at the infrared, the resolution is well, let's say good enough, not optimum, but at least good enough to work. The signal to noise ratio, so the sensitivity at about 1 micron, which is needed for some of the filters, is not that good, even with the newest cameras. But this is really improved in the last times with the new cameras available. Yeah. Besides, also for the UV, I have a Schmidt cassegram, so UV work is very disturbed by that. But I don't use barrels. I remove the cover slip from the camera, which also increases a little bit transmission in the infrared at the wavelengths approaching 1 micron. But it's not enough for the blue side of the spectrum. But for the infrared is good. I prefer to do that. So to remove the camera cover slip, camera window, and try to avoid unnecessary glass material in the path. Yeah.
And Antonio, when you showed the false color images towards the end, were those sharpened after your analysis for presentation?
No, they were sharpened for presentation. They were not sharpened to produce results. No, never. So I always have a non-sharpened and even not linear scaled version, an original version of the images. Those are the ones that count, yes. But that would not be at least as demonstrative as they should for a presentation like this. Obviously, no processing like that. Only calibration. Yeah.
Any more questions or comments from anyone?
I have a question for Christophe, because as you said, your work is fantastic and very important and interesting, but we have to think that lots of amateurs decided to use color cameras and will continue to use them, even only for the reason that some of the new color cameras are producing good images in the infrared past 800 nanometers. So it's a dual camera. Can you suggest or give rise to a tutorial to calibrate color cameras, to uniformly calibrate color cameras, at least with a given sensor, so they can be useful for longer time scale, year to year image comparison with regarding color changes? I'm not saying that, also that is as an addendum of your work to allow more people to be able to produce calibrated and useful and reproducible color images. Can that be done with a color camera with specific constraints or something like that?
I think it could be done, because now I am able to calibrate filters that are not non-photometric. I know how to do that now, thanks to a spectroscopy and not even photometry, not only photometry. But one problem would be to know exactly the pass bands of the filters that are located over the sensor of the color camera. So in general, this data is presented by the sellers, but it could be tried. But I don't know whether this kind of data is accurate or no.
Okay.
It could be interesting to do so for infrared, maybe, because the color cameras are more monochrome in infrared than in color, so it would be maybe easy. For example, if you want to try to calibrate methane band filter, I think it could be done quite easier.
Mm-hmm.
I see Steve has his hand up.
Yes, and I'll lower it now too. I have a question for Pat, which is, all of us in one way or another are kind of interested in retrieving real physical quantities of Jupiter's atmosphere. And, we've done what we can do up to a certain point. And obviously there are very sophisticated retrieval models like Nemesis. Are there any educational, or I'll call them, not in a disparaging way, toy sort of retrieval models that might be amenable to running on, personal computing systems that interested folks like us might be able to play with?
Yeah, good question. I mean, Nemesis is a bit clunky and not particularly easy to get up to speed with. I mean, there's something called PSG I've heard of, which is a Ford model I know, and I think has a retrieval module to it. I've never tried using it, but that might be amenable to that kind of thing. I mean, obviously, in order to do all this sort of work, you need to have you need a model of the atmosphere in terms of its pressure and temperature, and you need a model of the absorption coefficients of the different gases that are in the atmosphere. So you've got to get all those in place first, and then the retrieval process itself is, I mean, it's a fundamentally tricky problem in that there are many answers which will fit the same data, and so it's a sort of a horribly non-linear, ill-conditioned problem that you kind of need to. Sorry, I'm wobbling. The short answer is no. There's not a toy retrieval model out there that you can plug and play, because the process itself is remarkably ill-defined and ill-constrained, and so you need an awful lot of initial constraints and initial expectations in order to limit your solutions to ones that are plausible.
Okay, thank you.
If I could go back to Steve, just for one question. I mean, one potential use of all this is to be able to do fairly frequent observations, to see how things change and track things as well. And you seem to be definitely recording ammonia-rich plumes in the northern equatorial zone. I wondered if you had any recent observations of those taken just 2 or 3 days apart, so that you could see the same feature a few days apart and see how fast it's moving.
So the answer to that is no. And part of the reason is that I'm only, in my own mind right now, I'm only seeing that enhancement clearly associated with plumes with the absolute best data that I can look at, the highest resolution, the best seeing. On the other nights, most of the nights I have, they're too blurred and wiped out to really make them out clearly. So that's one of my interests in getting higher resolution data. Certainly frequently is great, but just being able to get higher resolution data, because we're not sharpening these images, and it's just hard to define that association without good resolution.
Well, the planet is moving north.
Yes, it is.
We have a question coming from YouTube, which is from Sylvia Korolik. I hope I've pronounced your name reasonably correctly. She has a question for Antonio about calibration, wanting to know if you can explain the steps.
So explain the steps of image calibration. Okay, so images are obtained. Calibration needs the presence of a satellite. Okay, something whose albedo has to be compared with that produced, with the albedo produced, Jupiter albedo produced with the different filters. And the exposure or a scaling factor is introduced to homogenize the albedo of the satellite. So that gives the first step of calibration. There is no need for what you call it dark calibration. For flat calibration, the absence of dust or irregularities of field has to be checked, but usually is not a problem. But what specific kind of calibration is the question about it? Is another kind of calibration?
The question just says calibration. I'll see if Sylvia puts in a follow-up comment in the chat or not.
I was just thinking about the calibration of color cameras, as Antonio mentioned that, and thinking that it's possible to calibrate any camera using a spectroscope, as Andrew will well know.
Yes, that was going through my mind as well, as to
if you took a spectrum of a known star that has a well-known spectrum and professionally established spectrum, and then compared it with what you got with your color camera, then you would have a measure of its sensitivity across all the wavelengths.
So yeah, it's a matter of either getting a spectrograph to someone with that camera, or getting the camera to someone with a spectrograph to do. And there are a wide variety of spectrographs and cameras out there, so it's possible someone's looked at it in the spectroscopy community. And the same goes with filters as well. It's possible to use one of the amateur available spectrographs to kind of check what the filter bandpass is.
It would probably be the same for various cameras that use the same sensor, I would guess. It would be a property of the sensor rather than the camera. I wouldn't have thought the camera electronics would alter that, but I can't be sure about that. So theoretically it could be done. How useful it would be, I don't know.
Yes, I'm trying to think if there's anyone who's done, I mean, Christian Briel has looked at a wide variety of cameras. I'm not sure if he's actually looked at the response though, particularly on colour, because in the spectroscopy community, it tends to be black and white cameras which are used. We have a follow-up from Sylvia, which is, which program do you use for calibration? She uses a black and white camera.
Well, the software I use for calibration is so to introduce those scaling factors is Maxim Deluxe. Maximium Deluxe is the software I use. So it can produce subtractions. It can introduce factors. It calibrates the images very well. That's the software I use for.
So the diffraction limited, yes. Maxim DL. Yeah.
Yes.
Yeah, and that comes in a variety of kind of levels, that sort of different functionality, doesn't it? So it's the deluxe one which you're using.
Yes, it's the one that allows cameras to be used. So yes, DL Pro 6.
Okay, we were thinking of closing 5 minutes ago. Would anyone like to continue any chatting any further, or should we actually draw this to a close now?
We've had a thank you from Sylvia coming on YouTube.
Well, I think I'd better just say thank you very much to all of the participants, to the speakers. Thanks to Andy for managing this Zoom chat. Thanks to Pat again for your contributions. And please continue conversations by email or other means. I'm sure we'll continue to be in touch as this topic proceeds. So thank you very much, and good night.
Thank you. Good night.
Thank you.
Good night.
Thank you for organising it, John.